Okay, you're all able to see the screen, right?
Yes, sir.
Okay, fine. Series RLC circuit, is it there on the screen?
Yes, sir.
Okay, fine. So because I wanted to start with the series RLC circuit. So today's um, class outline would be, first we'll be discussing about series RLC circuit, followed by a few numericals from RL and RC circuit. All right. So shall we begin?
Sir.
Okay. So other day, just a minute, let me start the recording. Yeah, I have already started. Okay. So yesterday we discussed about the working of RL circuit and RC circuit, right? So what we observed is that whenever we consider a practical inductive circuit, that is RL circuit, and a practical capacitive circuit, which is RC circuit, the power consumption is not zero. Instead, the average power consumed by them was Vm Im cos phi. Okay, that means to say every practical circuit, they consume some amount of power. Okay, so today let us look at the working of series RLC circuit. In case of series RLC circuit, the three elements that are resistor, inductor, and capacitor are connected in series. Okay, the application of series RLC circuit is in the communication field. So let's say, for example, you want to send a certain information at a particular frequency. So what we can do is we can send the information at the resonant frequency, because resonant frequency is unique for a given value of L and C. So say, for example, radio mid, say 91.5 megahertz is their band. So what they can do is, they can tune the circuit at a resonant frequency of 91.5 megahertz, and then they can transmit the signal. And being sitting at home, with an device called oscillator, which is actually there within your mobile phone itself, you can tune that frequency so that you will be able to latch on to the source frequency. So that's how we tune the radio transmission signals. So that is the major application of series RLC circuit. All right. So that being the application, now let's look at the working. Okay. So RLC elements are connected in series. A sinusoidal voltage source V is connected across the three. Capital V represents RMS value of supply voltage, and terminal voltage VR represents resistive drop. VL represents inductive drop across L, and VC represents capacitive drop across C. All right. And vector diagram. Okay. Now vector diagram becomes pretty interesting, because we need to handle the three voltages VR, VL, VC, and along with these three voltages, you need to handle the supply voltage V as well as supply current I. Okay. So in the previous lessons, we had seen that for a resistive element, VR and I are in phase. Whereas for an inductive element, VL leads I by an angle 90 degree. And for a capacitive element, I leads VC by an angle of 90 degree. So if we know this information, we can easily draw the vector diagram. Okay. Now, while drawing the vector diagram, initially I never spoke about the magnitude of VL and VC, right? So depending on the value of XL and XC, a series RLC circuit can have different values of XL and XC. Okay, that's because your XL is 2 pi FL and XC is 1 over 2 pi FC. So what if, in a particular RLC circuit, the inductive reactance is found to be greater than the capacitive reactance? What happens? When inductive reactance, if at all it is greater than capacitive reactance, we would say the series RLC circuit works in a kind of RL mode. That is, the circuit behaves like more of inductive circuit. Okay. And similarly, what if the capacitive reactance XC is greater than the inductive reactance XL? So obviously the capacitive element is going to dominate the inductive element. Under this condition, the circuit behaves in a kind of RC mode. All right. And you may also have a situation in which your capacitive element could be equal to the inductive element. In the sense, XL may be equal to XC. Okay. So actually, the third case here, I have made a mistake. It should have been XL is equal to XC, and this should have been KC, and this should have been KSB. Okay. All right. So case A, let us look at. So in case A, that is what I was referring to. We are assuming inductive reactance greater than capacitive reactance. All right. So when XL is greater than XC, VL will be greater than VC. That's simply because you must be knowing VL is given as I into XC and VC can be given as I into XC. Okay. When XC, sorry, this is I here. Okay. Now, when XL is greater than XC, it's quite obvious that VL would be greater than VC because it's a series circuit and current remains the same. Okay. Now, while drawing the vector diagram, what you have to do is first you draw the resistive drop VR and the circuit current I. They will be in phase. And next, you project voltage VL with respect to current I. Okay. The green line basically indicates the vector length of VL. All right. And inductive voltage VL leads current by an angle of 90 degrees. And next you project the capacitive voltage VC with respect to current. So capacitive voltage lags the current by an angle of 90 degrees. Hence, VC is projected in the downward direction. Okay. Now, you must observe, carefully the vector diagram. Okay. In the sense, if you observe closely, I have taken VL with a larger length and VC with a shorter length, simply due to XL is greater than XC. So when XL is greater than XC, VL will be greater than VC. So logically, you have to select the vector length. You select the vector length in such a way that VL is greater than VC. So that's the reason, VL is having bigger length and VC is having a smaller length. Okay. So we call this particular condition as RL mode of operation. That is, the circuit behaves like more of inductive circuit. Okay. Once we are done with projection of VR, VC, and VL, now let us consider the vector difference. If you see closely, VL and VC, they are antiphase vectors in the sense, with respect to current, they have 90-degree phase relationship, but they are opposite to each other. Okay. Since VL is greater than VC, you can take the effective vector difference as VL minus VC. Okay, so it is not difference of VL and VC, it is the subtraction of VC from VL. Okay, so VL you have to write it ahead of VC because VL is greater than VC. Okay, since inductive voltage is greater than capacitive voltage, so the difference in voltage, that is VL minus VC, is projected in the direction of VL. So the orange line basically gives the vector difference of VL and VC. And then the closing side of the triangle gives the supply voltage V, okay, which is nothing but the hypotenuse of the right-angled triangle. All right. So now the right-angled triangle is consisting of three sides: the adjacent side with vector length VR, the opposite side with vector length VL minus VC, and the resultant vector, which is nothing but the supply voltage V. Okay. Now, taking these three voltages in consideration, you can derive an expression for impedance. So analysis, okay, I'll come back to XC sometime later. The case 2, I'll come back to sometime later. Okay. So for case 1, that is XL is greater than XC, you can write the resultant voltage V as under root adjacent side square plus opposite side square. In the adjacent side, we have VR. So VR square we are going to take. And in the opposite side, we will have VL minus VC. Hence, we have taken VL minus VC the whole square. You just expand. And when you expand, you will be able to take out the current outside the square root. And in the end, you will be able to get V is equal to I into Z, where Z is called as the impedance of RLC circuit, and Z is given as R square plus XL minus XC the whole square. Okay, so that's about the impedance of RLC circuit working in RL mode. Okay, and phase angle, again the trigonometry you can use opposite side by adjacent side. So on the opposite side you have had VL minus VC, and on the adjacent side you had the resistive drop VR. So just substitute the respective drops. So you'll be able to get XL minus XC in the numerator and R in the denominator. Okay. So this is about the working of RLC circuit in RL mode. Okay, I'll stop at this juncture, and if you have any doubts, you can just let me know. You can.
So can you show the derivation again, sir?
Yeah, derivation. Okay. Yeah. In any right angle triangle, the resultant is under root adjacent side square plus opposite side square, like Pythagoras theorem. The same thing we have applied. You want me to bring that vector diagram over here? Okay, I've just placed it for better clarity. So x square is VR and y coordinate is VL minus VC. So VR square plus difference of VL minus VC the whole square. All right, can I go ahead?
Yes, sir.
Okay. All right. Okay. Now let's look at case 2. Okay. So in case 2, we are under the assumption that Xc is greater than XL. That is, capacitive drop is greater than the inductive drop. So when the capacitive drop is greater than inductive drop, you can draw the vector diagram as shown in figure B, okay, which is under the caption case B. Okay, the same vector diagram basically we have drawn, but while drawing the vector diagram, when Xc is greater than XL, what we have done is we have chosen vector length VL smaller than vector length VC, simply because VC is greater than VL. You can just make out the difference between case A and case B. Since VC, okay, which is nothing but this red line, okay, since VC is greater than VL, the difference needs to be projected in the direction of VC. So the vector difference is taken as VC minus VL. And this vector difference is being projected in the direction of VC. Okay. So once you have VC minus VL, what you can do is you can find the resultant, which is indicated by the orange arrow. Okay. And the angle between the voltage and current is taken as again phi. Okay. And if you were to apply the Pythagoras theorem in order to find the value of resultant, you will be able to get the following relation. Okay. The resultant being the hypotenuse, which is V, which is equal to under root x square plus y square, x being the resistive drop and y being the difference of Vc minus VL. And when you simplify, once again, you will end up in getting V is equal to I into Z. Over here, Z is nothing but this portion. This portion. This is my Z. This is my Z. Okay. So Z is under root R square plus Xc minus XL the whole square. So if you compare the impedance of case 2 with case B, more or less the representation remains the same. Only difference is that in case of case 1, we have had XL minus XC the whole square. In case of case 2, we have XC minus XL the whole square, simply because XC is greater than XL. Okay, so that's about the impedance. All right. Okay. Then finally, let's consider the third case. Okay. So in the third case, we have taken XL is equal to XC. Okay. Now, you see, your inductive element and capacitive element, they depend on frequency, right? Because their respective reactances are XL is equal to omega L and XC is equal to 1 by omega C. So what happens is that as you start increasing the frequency, initially XL may increase. Okay, that's because, okay, let me just demonstrate. Probably you know the theory of series resonance. Okay, XL is equal to 2 into 5 into F into L, and similarly XC is equal to 1 divided by 2 into 5 into F into C. All right. So what happens is that as you start increasing the frequency from 0 value, initially you will find that XL starts increasing and XC starts decreasing. That's because XC is inversely proportional to F. Okay. So as you go on increasing the frequency, at one particular frequency, which is called as the resonant frequency, the cancellation of XL and XC takes place. Okay, and that happens when XL is equal to XC. So when XL is equal to XC, what happens is that you will get the vector length, equal vector length. I mean to say equal vector length. That is, VL length matches with VC length. And VL and VC are two antiphase vectors. So when you take out the difference of the two antiphase vectors, you will get the vector difference as 0. So due to which the cancellation of VL with VC takes place. And hence you will be getting only the resistive conditions. That is, you will be left with voltage VR and current I. So which is nothing but the response of a pure resistive circuit. So under resonant condition, when XL is equal to XC, your series RLC circuit behaves like a resistive circuit in which the voltage and the resistive drop are in phase. Okay. So even V also you can project. Okay. So V is nothing but the resistive drop. There is no other element left in the circuit. So V is equal to VR for case C. Okay, and this case C is also called as the resonant condition. Okay, so that's all about your series RLC circuit. And if you look at the voltage and current equations, okay, voltage equation by default we assume that V is equal to Vm sine omega t, and current equation can be written as Im into sine of omega t plus or minus phi. Now plus or minus phi is considered. Okay, so plus phi is for RL mode and minus phi is for RC mode. Okay, so in RL mode the voltage leads current, and in RC mode current leads the voltage. Okay, so on that note, the plus and minus signs are chosen while representing the current. Okay. So that concludes the working of series RLC circuit. Any doubts you can please ask. No doubts? Okay, if you have no doubts, then I can go ahead with the problem. So what I want you to do is, be ready with a pen, paper, and a calculator. So take about 1 minute to arrange the stationery. Okay, pen, paper, and calculator is must. Okay. Screen is frozen for some reason. You're able to hear me?
Yes, sir.
Hello? Did I lose? Did you lose me? Or you're able to still hear me?
No, we can hear you, sir.
For some reason, you know, my screen is frozen. I don't know.
Try restarting.
I'm not able to come out of it.
Task manager and close it. I think PowerPoint isn't responding.
Okay, just a minute. I'll just let me quit and let me start over again. Just give me 5 minutes.
Okay, sir.
Yes, sir.